Hello everyone. In this video I'm going to be covering sections 4.1 and 4.2. So these are getting into solving systems of linear equations in two variables. What we've been doing is basically solving one equation, right? So a system is going to look like this, just to give you an idea visually. But a system is at least two equations. And specifically the systems that we're going to be concerned with initially. Later on in the semester we'll talk about nonlinear systems, but for now we're going to talk about systems of linear equations. So meaning two lines. We're going to be looking for a solution to a system of two lines. So what might that mean to have a solution to a system of equations? Right? We'll need to talk about that as well. Way back when, I think it was on page 15, I said there were a couple problems such as this. This is on page 15. And I said, oh, we'll come back to this in chapter 4. And that's what we're doing now. So we are in chapter 4 now. So we can solve those types with the material that we're seeing today. So yeah, let's read a problem. What we're going to do is read this word problem actually, and then just set up the system of equations. And then what we'll do is actually we'll solve a different system just to get used to solving the system. And then we'll come back and solve this in a bit. So this says in 2016, there were 96 species of birds in the United States that were considered threatened, meaning likely to become endangered, or endangered, meaning likely to become extinct. The number of species considered threatened was one more than 1/4 of the number considered endangered. So we have kind of a mathematical statement here. So considered threatened was one more than 1/4 the number considered endangered. So that's fairly mathematical there. We'll dig into that. It says write a system of equations that models the number of U.S. bird species considered endangered or threatened in 2016. So what I recommend with all of these is to read and reread. So with word problems, that is. So read and reread. So let's go ahead and reread this. So I'll just read through it again. It says in 2016, there were 96 species of birds in the United States that were considered threatened or endangered. So what they're saying is that this 96 accounts for types of birds that are considered threatened or considered endangered. We don't know how many. So I'm kind of just getting a picture. There's 96 species. Over here, there are threatened types. Over here, there are endangered types. And we don't know how many of each. But basically, we know if we add them together, we get 96, right? I'm just trying to sketch out what we have. We don't know if it's like 90 and 6. We don't know, right, if it's 50 and 46, or if it's 95 and 1, right? There's all those combinations that it could be to add up to 96. And we don't know yet. But this type of equation, right, is kind of getting us to what we need to do. So actually what I'm going to do, is set up a variable. So I'm going to let x represent the number of threatened. And then I'm going to let y, and I know I'm using this weird symbol, it looks like an equal sign plus a little bit more, but it just means defined as. So this symbol just means defined as. So I'm going to let y represent the number endangered. Okay, so with that, I'm going to kind of leverage this sketch. So I'll say x, the number threatened, plus y, the number endangered, would equal 96, right? Just from the given information. So that's one equation involving the information. And actually that equation is from the first sentence, really, right? The 96 considered threatened or endangered. The other equation, so we're going to need another equation to make a system. It looks like there's this information we haven't used yet. So the number considered threatened was, right, is 1 more than 1/4 of the number considered endangered. Right, so from this sentence here, the number of species considered threatened, for us, the number of species considered threatened is called x. So I'll say x equals, right, and I'm saying x equals because we have threatened, right, was, so we have like x is equal to something that we're mentioning over here. So 1 more than 1/4 of, 1/4 of the number considered endangered would look like 1/4 y for how we defined things, right? Here's the endangered variable. 1/4 of that means 1/4 times that. And then 1 more, right? So 1 more than that would mean, okay, now I need to add 1. So this right here would be the system of linear equations, you know, with this definition that describes the scenario. And in a little bit, we'll learn the skills that it takes to solve this system and actually figure out how many go here and how many go here. But for this initial problem, just to get used to kind of doing this a piece at a time, we were just tasked with figuring out the system, not fully solving it. So read and reread. Kind of what we did second was assign variables to the things you're looking for, right? That's what I did here. So read and reread, that's kind of going on in here. And then this was my part 2. This is what I mean, is I assign variables. And then kind of part 3 is write equations. Involving those variables. Okay, so part 3 for me was happening right here. And in a later part, we didn't have to do this right now. We're going to solve the system eventually. So let's see a problem that is actually not tethered to anything specific, like, you know, a number of birds or anything like that. We just have a general system here. We have 3 times a number plus another number is 5. We have that same number, that first number. If you subtract 2 times the other same number, then you get 4. So we have just kind of a little puzzle, numerical puzzle here. Solve the system by graphing. So graphing is going to be our first way of doing this. We're going to learn a few different ways to solve the system. So we'll see graphing, and we'll see that it's not a great way. The second way we'll see, I believe on this next page, yeah, we'll see substitution next. And then I believe our book calls it elimination after that. So we'll see these different ways of solving a system. Okay, so the first way will be this graph. So how do we graph lines? So the first thing I want to do is graph this thing right here. So I'm going to choose to put this into slope-intercept form. I'm noticing that the y is already alone, so it's pretty easy just to bring over this 3x And I'll say this first one is equivalent to y equals negative 3x plus 5, right? And with it in that form, I can find the y-intercept right here at 5. And then I can use the slope of negative 3, which is equivalent to negative 3 over 1. In other words, our rise is actually a fall of 3, and our run is a run of 1. Right, so that was from 5, 1, 2, 3, and then over 1. And then do try to use a straight edge of some kind. I just have this external hard drive. This is the best I could do right now, but I'm just using some sort of straight edge, right, to make a fairly straight line, because we're using our graph in this case to solve this. So you want a fairly accurate line. For the other one, maybe I'll do this one in red. Yeah, I mean, I can get this into slope-intercept form again. Maybe I'll just stick with a similar approach. So I'll try to get y alone. So I'll go ahead and subtract x over, actually, as my first move. So I'll have negative 2y equals negative x plus 4. And then I'll go ahead and divide by negative 2 everywhere. So I have y equals, so I'll just actually write this negative x over negative 2 as positive 1/2 times x, just to make it clear what my slope is. And then 4 divided by negative 2 is negative 2. So this would be our other equation, this equation, just written in slope-intercept form, right? Where we can see the slope is 1/2 and the y-intercept is negative 2. So I'll go down here to the y-intercept. And then in this case, our rise is positive, so we'll go up 1, and then I'll go over 2. And I'll just make a fairly nice line. It's never going to be perfect when you're doing this by hand, but that looks pretty good. So solve, right? That's what the question was, or the requirement was. What does it mean to solve a system? That's kind of the conceptual piece we're at now. I encourage you to think about what it means to solve a single equation. Right, so what does it mean to solve like this equation right here? So if we look at the red one, this is a solution to that equation, right? That point is 0, negative 2. It's specifically the y-intercept, right? I just picked it for no good reason. So what does it mean to be a solution? Is, first of all, you're on the graph. What does it mean to be on the graph? It means you provide a true statement when plugged in, right? So it should be that negative 2, right, I'm plugging in negative 2 for y, should equal 1/2 times 0, right, plugging in 0 for x, minus 2. This should be a true statement, or else this point is not on the graph because it wouldn't be a solution to the equation. In summary, right, and you can see here negative 2, yeah, negative 2. In summary, if you're on the graph, if you're a solution to one of the equations, that means you live on the graph, right? What does it mean to be a solution to the other equation? It means that is the graph, right? If you're on the graph of the other equation, it means that you solve, or you provide a true statement to the other equation, right? If you plug in any point into this equation on the blue line, then you get a true statement. However, there's one specific point right there that it appears lies on both lines. Okay, so a solution to the system, this question, really means find, if any, a solution that lies on both lines, right? A point that lies on both lines. So a solution to the system should provide true statements in both of the equations. Okay, so that's what we'll check now. What is your best guess at what this point is? So my best guess, I believe, would be 2, -1. So what I'll do is I'll check 2, -1 in both of these equations. If this is indeed the solution, then we'll see true statements for both. And that would be the only point that would provide true statements in both. So let's do that check here. So 2, -1, that means I'm plugging in a 2 for x. So I would have 3 times 2 plus -1, are you equal to 5, right? So I'll put a question mark. Are you equal to 5? What did I just do? I'm plugging in this point into this first equation here, as it originally was. So 3 times my x, here's 3 times my x, plus the y, right? Is this true? 6 plus -1, is that 5? Yes, that is. Right, but we need it to be true in both to be a solution to the system. So I'll go ahead and check it in the other one now. So is it true that 2, right, plugging in this point to the other one, minus 2 times -1 is equal to 4? Well, 2 minus 2 times -1, this turns into addition. A negative times a negative is a positive. So this turns into 2 plus 2 is 4, which is true. So this indeed is the solution to the system. So if there is a solution, then the solution to a system is a point, all right? It's not just an x or a y, it's an x and a y. All right. Okay. I'm going to move to substitution now. So that was graphing. Graphing doesn't always work great. It's not always easy to see what the solution is, right? What if our solution is weird? Like, what if it's not 2 and -1? What if it's 2.16 and -1.04? Then it'd be difficult to see that from a graph, right? So in those cases, we often lean on a different method, some algebraic method, in which the solution will just kind of arise rather than us needing to infer it from our handwriting. So substitution is this algebraic method, or it's one of them that we're going to see, and it's a accurately named method. We're going to substitute in some way one equation into the other. So what I mean by that in specific, so check this second equation out. It's not always going to be the second equation, by the way, but in this case, we have x equals y plus 1. So this equation's telling me for this system, and sometimes you'll see systems noted with this brace, the single brace. Anyways, x equals y plus 1 is telling us, hey, you can either use x, or wherever you have an x, you can use y plus 1. Why? Because they're equal. That's what this equal sign is telling us. So in the first equation, where I have an x, I can replace that with a y plus 1. So I'll go ahead and do that. That's substitution in a nutshell. And this is available to me because x equals y plus 1. So where I had x before, I'll write y plus 1 plus y equals 4. This is the first equation where I have replaced x with y plus 1. Now you have one equation with one unknown, and you can solve for this. So let's do that. So y plus y is 2y, plus 1 equals 4. Subtract the 1. So 2y equals 3, divide by 2. So I'd have y equals 3 halves, actually. So that would be the y component of our solution, actually. And then what do we do with it? One option is we can now take this y and plug it in right there for y. Why? Because then we could just add 1 to it and we quickly get x. So I'll go ahead and do that. So x would equal 3 halves plus 1. Right? 1 is the same as 2 halves in terms of a common denominator. So 5 halves, right? If you have the same denominator, you add numerators. Or you can throw this into your calculator, of course. I'm not going to do that, but. So x would equal 5 halves. And our solution, I'll write it as an ordered pair. Our solution would be 5 halves, right? That's where x goes. And 3 halves. As a check, I'm not going to do it here, but I encourage you to pause the video. Go to Desmos. Okay? And type this system in. In one row, type this one. In another row, type this one. You should see that they intersect at 5 halves and 3 halves. Desmos might call this 2.5 and 1.5. Okay, but that's a good way of checking these. You should see an intersection here, or else I did something wrong. Please let me know if I did. So I'm going to go quickly on to the third method. Substitution, I'll be honest with you, is my favorite. So I do encourage you to use substitution. Let me just give you a little bit of guidance on this next one. I'm going to leave this for you. But the difference between this one and the one I just did, or a difference, is that none of the variables are completely isolated from the get-go. Right? Here, I had x equals. In other words, x was isolated from the start. Here, you just need to do a little bit of work. And you can make any of the choices available, right? You can isolate this x, you can isolate that x, you can isolate that y. I would prefer to isolate that y just because it'll be the easiest of those 4 choices. So I'll get you going on this one. So we would have the first equation as y equals negative 2x plus 6. And then this thing can replace y. After you make that replacement, you'll be able to solve for x. After you find x, right, you'll find some x equals some number, plug that number in here, and then you'll be able to find y. So on to elimination. Again, it's accurately named. It's a good title. With this technique, we want to eliminate one of our unknowns. If you think of it, that's really what we're doing in this stuff too. We're kind of eliminating one of our unknowns through substitution. Here, we're going to eliminate one of our unknowns through addition, really. So sometimes this is called the addition method, by the way. So elimination and addition method is kind of synonymous. What I'm going to do is just add these equations together and see what happens. Okay, that's why it's sometimes called the addition method, because we get the elimination to happen through some type of addition. And I'll show you what I mean by some type of addition. So if I add as is, in this case, let's see, so what I'm adding are these like terms, right? So I get a 4x, negative 7y plus positive 7y. That's 0y, so I'm just not going to write anything there. And then I have equals 3 minus 2, or 3 plus negative 2. That's a 1. So in this case, that addition did directly eliminate one of the unknowns. So that was really good. That doesn't always happen. What's great about that is I can just divide by 4 now, and I know x that quickly is 1/4. The x that solves this system needs to be 1/4. So I know that. Let me show you what you can do. I'm going to write the same system, because now we want to learn y. Okay, so now we want to kind of do a similar thing, except the result of this work, we want to learn about y, right? We learned what x was here, and now we want to learn what y is. So I want to eliminate x this time. So if I add them together, obviously x won't be eliminated. We'll still have this x, and we'll do the exact same thing that we just did. So something you're allowed to do, though, is you're allowed to multiply these equations by any non-zero number. So multiply by any non-zero. So it can't be 0. And you're allowed to multiply one equation or the other or both. And they don't even have to be the same numbers. You can multiply this equation by 2, and you can multiply this equation by 7. Or you can multiply this equation just by 6, right? So you can do any of that. You can't multiply any of these by 0. So the number, kind of, if you're thinking, okay, now what number? There's a lot of non-zero numbers. We want to choose a number such that when we multiply one of these equations by it, we accomplish the goal. And the goal is to eliminate x right now. So if the goal is to eliminate x, and we have a 6 here and a negative 2 there, well, if I had a negative 6 here and a positive 6 there, then elimination would occur. So what number is necessitated by wanting a negative 6 here? So 3. So I'm going to multiply through. I have to do it on both sides, by the way, by 3. So that'll transform this system into negative 6x minus 21y equals 9. Right, that's the first equation multiplied by 3. The second equation, I'm not multiplying by anything. And now when I add, good things happen. Right, the x's cancel away. Negative 21 plus 7, what is that? Negative 14y equals 7, right? 9 plus negative 2. Divide by negative 14. So y would equal, well, 7 divided by negative 14, we can write that as negative 1/2. So we have our solution now. It's x, and I'll write it as an ordered pair. And y was our negative 1/2. right, that's elimination method, also known as the addition method. So you're allowed to multiply by any non-zero number as many times as you want in order to have opposites, right? That's when good things happened. So these y's eliminated because they were opposite. The coefficients are opposites. Eventually, when the x's were able to cancel, it was because they were opposites. So this move that you're allowed to make, you're making it with the intent to build opposites so that you get an elimination to occur. Okay, I'm just trying to kind of summarize. I'll leave this next one to you, but just know this should have been different. This should be 3x plus 4y equals 4. I should have had an equal sign, not another plus sign. So it should be this system for part 2 here. Yeah, so this will be the last one I do in this video. This is 4.2 now, where we're using the idea of solving systems within the context of word problems. Oh gosh. So that can be a lot, and it's totally doable with practice. So what I'm going to do is go back and look at the example 1 from these notes. That was where we wrote this system involving these birds. Okay. So I'll write this system down and then we'll solve it. So we had x plus y equals 96. And then I believe we had x equals 1/4 of y plus 1. It just says solve. It doesn't say by any particular method, right? So as I said earlier, prefer substitution, especially in a situation like this where one of the variables is already alone. So I'm going to replace x with 1/4 y plus 1. Right, I've substituted that second equation into the first. 1/4 y plus y. So if you want to use your calculator to help you do this arithmetic, please do. So 1/4, and then I'm adding the coefficient, right, just 1. So that's 5/4. And solve for y. I'll just think of it as division by 5/4. You can multiply by 4/5. So here I'll just type this one in. So I'll put 95 up top of a fraction, and then I'll scroll down and type another fraction and put the 5/4 there. 76. So we just learned, well, let me remind ourselves what y was. That was the endangered. Okay, and then once we learn that, we can go ahead and plug 76 right here. And for y, take 1/4 of it, add 1, and then we get x. Or you can plug y in right here and then subtract it over, right? It looks like it should be 20. Either way you want to think of that. So I'll just do the second thing actually. So x plus 76 equals 96. So I can actually solve that just visually and say, oh, x needs to be what? What number plus 76 is 96? That should be 20. And that would be threatened. that's it for this one. Talk to you next time. Bye-bye.